මේක ලියලා කියන්න තමයි ආයෙ පස්සෙත් තහනම්. Properties of matter. Right. So go to experiment 5. Write down determination of determination of Young's modulus of a steel wire. 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 Young's modulus of a steel wire. Right. Listen, may I read it? Right. May I read it? First, we have to have right two wires made of the same substance. Right. First, we have to have two wires made of the same substance. Right. Two wires made of the same substance, and both wires are going to suspend here at the same supporter. Right. Same supporter. If that is at the ceiling, then it will be close to each other at the ceiling. Right. It is suspended. Then this is the first wire. Right. Here we have suspended. Suspended. And for this wire, right? For this wire, a fixed mass is attached. Right. A fixed weight or fixed load is attached. Right. Fixed load is attached taken here. And for this wire, right, we connect the main scale. For this wire, we connect the main scale. We connect the main scale for this wire with the fixed mass. And this is the next wire that is next to this, right? Next to this, that is made of the same substance, right? Made of the same substance. And for this, the tray is also attached because we are going to change the load, right? The tray is also attached because we are going to change the load, right? We are going to change the load. Tray is also attached, right? And for this, a vernier scale is fixed. For this, a vernier scale is fixed. Right. Okay. Now this is the main scale. This is the main scale. This is the vernier scale. Right. And this one is a fixed load. Fixed load. Right. And this is the variable load that we are going to change. Variable load. Right. Now, listen. The reason to attach a vernier scale and main scale is when it comes to extensions, they are comparatively very small values. Right. Since they are small values, right, to take that reading accurately, vernier scale is attached. And main scale is millimeters. Vernier scale is divided into 10, then the least count is going to be 0.1 millimeters. Right. But we can go with the higher accuracy as well with the required millimeter. Right. Unless otherwise, this is a millimeter scale, main scale is a millimeter scale, and vernier scale is divided to 10 divisions. Right. Maybe. And then after adding a weight here, right? Before adding any weights here, first you have to take the initial reading. Before adding any weights here, right? When this is empty, first you are adding reading, right? And then adding weights, and when we add weights here, we are adding 500 grams weights at once because they are steel wires and it needs kind of a higher load to extend, right? So they are 50 grams, 100 grams, right? Minimum we had 500 grams at once, right? Half kilograms, 0.5 kilograms, right? At Kerala. Then you take the reading again from the main scale and vernier scale. Reading again, and that second reading minus initial reading is the extension of this wire, right? Because this won't be extended the way that is a fixed load. It won't be extended, right? Calculation purpose. This is to compare this with this. when taking readings. Right? And we are going to do the calculation based on this second file. Based on the second file. Right? Then from Young's modulus we know, we know F over A equals Y times E over L. Right? Now, if the initial length of this wire is L, right? Make initial length again, right? Say that is capital L. F is here, right? F is here. Then when this rate is mg, right? Say the diameter of the wire is d. Then phi r squared d over squared y e can be taken from this over L. Now, from this one, what we can change is m. Right? When m changes, what is going to change from the other side is extension. L is a constant, y is a constant, diameter is a constant, y constant, e constant. Right? Then when m changes, e changes. Right? Then m is going to be used as the independent variable. Right? Subject m. Now, this is mg equals, right? Phi d squared and then the y e over L, right? Then equals 4gl, right? Equals 4gl over phi d squared y, phi d squared y. Right? Now we can draw a graph between this and extension. And the graph is y equals mx between E is in millimeters, right? Then mass is in kilograms. Gradient of graph is 4gl over phi d squared y, right? Now 4 is 4, g is known, L initial length can be found, right? To find initial length, you can use the finger rule. Right? Initial length is a length here, a vernier scale going on, right? This can be like 4 meters, 5 meters, whatever. Yeah, because when we take a lengthier wire, extensions are also significantly increasing. Right? That's why. Otherwise, extension then that's it. So length can be measured using a meter ruler. Phi is known. D diameter of wire. To measure diameter of wire, they are using a microdisc gauge. To measure diameter of wire, then if everything is known, right, using gradient, y can be determined. Right? Y is something there now. So y is make gradient m dash, say that is m dash because I used m here already. Right? I'm going to replace that dash here now. Then y is given by 4gl over phi d squared m dash, like this we get 0.5. Right? Make an experiment about that, but the background that you need to know about the experiment is, right, a little bit more. Right? They have used the negative now, the benefits good up there. Right? They have used the negative benefits good up there. Right? But again, now sometimes when this is loaded, right, this point will be stagnant. Right? Then we have here, this is going to stagnant. Here, right? Even if there is set, when both are there, both are going to go down. Right? Then those cells are minimized. Right? Those cells are minimized. And if there are changes of length due to temperature increases or temperature, when we do this in the environment, what is happening? Right? Then both extends together, then there won't be any error coming into the calculation because of cleaning expansivity. Right? Benefits here. Vernier scale, main scale, readings and we are using two for different other readings, different other reasons. Right? We'll see them in the next part. Right. First, mention the materials. Right? On the materials, both here and mention the materials. mention the materials again. Okay, mention the materials. And two uniform, two uniform, two uniform steel wires, two uniform steel wires, two uniform steel wires. Within brackets, about 3 meters long, about 3 meters long. Length of the range and lazy, about 3 meters long. Height 3 to 4 meters, about 3 to 4 meters long. With a diameter, about 0.5 millimeters. With a diameter about 0.5 millimeters. Right. Next, main scale calibrated in millimeters. A main scale calibrated in millimeters. A main scale calibrated in millimeters. Next, a vernier scale. Next, a vernier scale. A vernier scale. Then a pan, a pan, a pan. Then a set of 0.5 kilograms weights. 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 Right? Then a meter ruler, a meter ruler, a meter ruler. A micrometer screw gauge, a micrometer screw gauge. Right. Alright. Then as the apparatus, take it down. Apparatus. Right, pan. No, this is the pan. This is the pan. And this is the supporter. Right, medium. Later along the supporter. And you will be getting two questions from modulus and Jager's method in next two papers coming up. Right? This is Karana Tekar. Here I have on giver. What is that? No, Bayar na smoke na kari. Sound lagi lagi. Yeah, we can do it. Okay, take out. Hello, cool, I got it. Support a main scale, vernier scale, fixed load, fan, variable load. Hello. Right, finish. Hello. Hello. Okay, then theory. Theory. Write out. Write out. If suspended mass is, if suspended mass is, if suspended mass is symbol M. If suspended mass is symbol M. An extension of the wire is symbol E. Right, put a comma and start from here. And measure it up to this point. Oh. Very good. Now, like that. I don't know if I didn't know. And you got only 28 days. Right, 8:30 a.m. just after 28 days, right? You are ready your hands, right? And why are ready 8:30 and 1:30? You are ready 5 hours. Right? Huh? Okay, okay, next. Okay, let's go to method. Right. Discuss let's go to method. 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 First one. First one. Suspend two steel wires. Parallel to each other. Suspend two steel wires. Parallel to each other. Suspend two steel wires parallel to each other. From a same horizontal border. From a same horizontal border. Right. Label these two wires as A and B for the ease of explaining. Right. Then I refer these two as A and B. Right. Label these two wires as A and B. Label these two wires as A and B. Right. Next point. Suspend the fixed mass, fixed load. Suspend the fixed load. Suspend the fixed load. Suspend the fixed load to wire A. To wire A. As it is well stretched. As it is well stretched. As it is well stretched. Next point. Next point. Connect the main scale. Connect the main scale. Connect the main scale. and the range scale. To higher A as shown. To higher A as shown. Next, attach a pan, attach a pan to the end of wire D. Attach a pan to the end of wire D and connect the vernier scale and connect the vernier scale. Within brackets, attaching the vernier scale closer to attaching the vernier scale closer to attaching the vernier scale closer to bottom end closer to bottom end of the wire B, bottom end of the wire B is more convenient is more convenient when finding extensions is more convenient when finding extensions. Right. Next point. Add a mass of 0.5 kilograms to the pan. Add a mass of 0.5 kilograms. Add a mass of 0.5 kilograms. Add a mass of 0.5 kilograms to the pan. And take the reading and take the respective reading using scales. Within brackets, the difference between final reading and initial reading. The difference between final reading and initial reading. The difference between final reading and initial reading. The difference between final reading and initial reading gives extension. The difference between final reading and initial reading gives extension. Right. Next point. Keep adding weights. Keep adding weights. By 0.5 kilograms. By 0.5 kilograms each. By 0.5 kilograms each. And repeat the experiment. Repeat the experiment. Right, listen. Right now, while recording, now we are adding the weights. Now, while we are adding the weights, now you have got the readings of the extension, right? And we are going to end the experiment just after taking six readings by adding weights, right? Then what we do is we are removing the weights again and getting the readings again, right? Remove right? The reason is to have a more accurate value extension, right? And if there are any bends in the wire, some are bends, very nice because this is a thin wire. Since there is a thin wire, right? Since there is a thin wire, if there are bends in the wire, sometimes when the load is at the bends are stretched, right? The bends are getting straight, right? They have bend the wire, they are become bigger. Now in the wire, right? Then the wire will be going here. Right? By binding wires are everything, and now when the load is there, these are going to sometimes stretch. Right? Then to minimize such errors, right, we are unloading the system as well. Right? Load the bigger yes, unload. Hello. That's you are here. Unloading never going Sandaruwan when you are unloading, you are getting a difference in the initial rate. A higher value. But again, may mark a window again. I mean, then the other thing is finally you can make sure that wire B is still within the elastic limit, right? Whether it has exceeded the elastic limit, because if that has exceeded the elastic limit, when you are adding weights, right? This means the whole experiment is wrong because Young's modulus is valid only up to elastic limit, right? Young's modulus is valid only up to elastic limit, right? Now in the when this returns back to the initial position, right? Initial weight, right? Initial reading will be approximately equal with the initial reading that you have taken before, right? If yes, which means that is within the elastic limit, right? Then you have to replace by and do this again, right? If you have exceeded the elastic limit, okay. Then next point. Repeat the same. Repeat the same. Repeat the same. Repeat the same. By removing the added masses, by removing the added masses, one by one again, by removing the added masses one by one again. Right, next. Calculate the average value. Calculate the average value. Calculate the average value of extension. Calculate the average value of extension. Obtain when loading and unloading. Obtain when loading and unloading. As the final extension. As the final extension. Right. Now, this is how our variable looks like. Right. This is how our variable looks like. Right. Masses are here. Right. Masses are here. And the scale readings, right? When it comes to scale readings, right? Again, we have two when adding masses and removing masses. Adding and removing. Right. Say these masses are initially 0, 0 means when only the band is attached. When only the band is attached. Right. Then 0.5, 1, 1.5, 2, 2.5, 3. Right. Likewise, minimum 6 reading we need. Minimum 6 reading we need. And if these readings are known, right? Now we can get the extensions. Extensions and two extensions also, right? Extensions. Again, when adding and removing. Right? For example, this is R0, right? R1 dash, we have R1, R1 dash, and extensions E0, E0 dash, E1, E1 dash, and this is the average extension. Average extension. Right. When away, table load. Right, take down. Right. Take it out. Okay. Yeah. Mass scale reading, mass scale reading, adding, removing, extension, adding, removing, average extension. There, mass scale reading, adding, removing, extension, adding, removing, average extension. Mass scale reading, adding, removing, extension, adding, removing, average extension. Right? Right? So at the end, what we need is average extension. Correct? Correct. How much measuring parameter man? Somehow with diameter. Diameter also. Correct? X point. X point. Take diameter. Take diameter. Take diameter. In two perpendicular directions. In two perpendicular directions. In two perpendicular directions. At three different places. At three different places. Two perpendicular directions. Two perpendicular directions at three different places. At three different places. On the wire. On the wire. And get the average. And get the average. And get the average as final diameter. And get the average as final diameter. And get the average as final diameter. Right. The final diameter is d1 plus d2 plus d3 over 3 in this. Right. Next point. Measure the length of wire. Measure the length of wire. Measure the length of wire. Measure the length of wire using meter ruler. Using meter ruler. Measure the length of wire using meter ruler. Right. Next. Plot the graph. Plot the graph. Plot the graph. Plot the graph Plot the graph between E and M, between E and M, between E and M, between E and M, and find its gradient, 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 and find its gradient. Next point. Calculate y, calculate y, calculate y. Calculate y as mentioned under the 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 right. So that's it. But there are like other minor things, but the important things to be discussed. Write down the marks. Like experiment there, you are sitting here and over the marks. Write down. First of all, thin wires should be used. Thin wires. Thin wires should be used. Thin long wires, thin long wires should be used. Thin long wires. Thin long wires should be used. Should be used to get a considerable extension. To get considerable extension. To minimize fractional errors. To minimize fractional errors. Fractional errors. Right. Next one. Both wires should be fixed together as parallel to each other. Both wires should be fixed together. Both wires should be fixed together. Both wires should be fixed together. Parallel to each other. Parallel to each other. Right. Next point. Next point. Following benefits are they are when using two wires. Following benefits are there when using two wires. Right. Under that first one. Errors due to sagging. Errors due to sagging / yielding. Errors due to sagging / yielding. Sag වෙනවා කියන එක දන්නවනේ. right? මෙහෙම වෙනවා කියන sag කියලා. මේක මෙහෙම වෙනවනේ කියන sag කියලා. Sagging. Errors due to sagging and yielding of supporter are minimized. Of supporter are minimized. Right. Next point. Errors due to linear expansion. Errors due to linear expansion of wires when temperature changes. Are removed. Are eliminated. Are eliminated. Right. Next point. Extension should be taken while loading and unloading. Extension should be taken while loading and unloading. Extension should be taken while loading and unloading. Prove that following experimental errors can be identified. Prove that following experimental errors can be identified. Prove that following experimental errors can be identified. Right. First one, right, mention one by one. Right, there are errors here. First one. First one. If they ask any slip, slip slash displacement at connecting points of wires at connecting points of wires and scales wires and scales next one if there's any bend is straight if there's any bend is straight in the wire. Next one. So, can make sure if the wire is within the elastic limit. Can make sure if the wire is within the elastic limit. Right. Next point. If there's a sudden change, of extension, if there's a sudden change of extension, is noticed when taking readings. It can be due to straining a bend. It can be due to straining a bend. Straining a bend. Can I don't tell them. They don't have any. Bends here, they might again, they are thin wires. No, they wires, they have only bends, right? Load down, they bends together. Right? There are extension and the point. Hello. Otherwise, extension is linearly very, right? After there, extension they are going to when there is say 1.5 1 millimeter for 1.5 2 millimeters, near 3 millimeters, or more. Then I go over about 6 or Anna, when right? Next point. If fire does not returns, if fire does not returns, back to its initial length, returns back to its initial length. After removing all weights, elastic limit is exceeded. Within brackets, have to redo within brackets, have to redo the experiment. I have to redo the experiment with another. I have to redo the experiment with another new wire. I have to redo the experiment with another new wire. I have to redo the experiment with another new wire. Right. That's it. About Young's modulus. Any questions? Right. What do you do experiments? I then again ignore it. Any questions? Quickly. Data R any questions about Young's modulus? Any questions? Never I am going to say no. Okay, is it clear? Any questions? Right, all good. Alright. Okay, then online. Are you all good? Online, are you all good? Right. Then let's go to question. Done. Alright. Okay. Experiment 6.